Welcome back to the second and final module of our course on structural analysis. In Module 1, we established the fundamentals of structures, supports, loads, equilibrium, internal forces, shear and moment diagrams, and deflections. Those principles are essential when dealing with statically determinate structures, where the number of unknown reactions and internal forces does not exceed the number of available equilibrium equations. But in real-world engineering, most structures are not determinate. Buildings with multiple stories, bridges with continuous spans, rigid frames, and arches often have extra supports, redundancies, or constraints. These are statically indeterminate structures. They cannot be solved by equilibrium alone, and require advanced analytical techniques. In this module, we will explore the analysis of indeterminate structures, methods like slope deflection and moment distribution, energy methods, influence lines, stability concepts, and the role of computers in structural analysis. By the end, you will be equipped with both the classical and modern perspectives on analyzing real-life engineering structures. 1. Statically indeterminate structures. A statically indeterminate structure is one in which the number of unknown reactions or internal forces exceeds the number of available equilibrium equations. For example, a fixed beam has 4 reaction unknowns, 2 vertical forces and 2 moments, but only 3 equilibrium equations are available. A 2-span continuous beam has more unknowns than equations. To solve such structures, we need to bring in additional information, compatibility of deformations. In simple terms, this means that the deflections and rotations at various points must be consistent with the physical constraints of the structure. Indeterminate structures have both advantages and challenges. Advantages: they are stronger, more stable, and provide redundancy. If one part fails, loads can redistribute. Challenges: they require more complex analysis and can develop internal stresses due to settlement, temperature changes, or fabrication errors. 2. Methods of analyzing indeterminate structures. Over the years, engineers have developed systematic methods to analyze indeterminate structures. Let us review the most important ones. 2.1 Force methods, flexibility methods. Here, redundant forces are treated as unknowns. Equilibrium equations are written, and then compatibility equations based on deformations are introduced. These equations involve flexibility coefficients, which express displacements due to unit loads. Example: in a propped cantilever beam, fixed at one end, simply supported at the other, the redundant reaction at the prop is calculated by enforcing the compatibility condition that the deflection at the prop is 0. 2.2 Displacement methods, stiffness methods. In displacement methods, the unknowns are displacements, such as rotations or translations at joints. Equilibrium equations are written in terms of these displacements using stiffness relations. This approach is the foundation of metric structural analysis, which is used in computer programs. 2.3 Slope deflection method. One of the earliest displacement methods, it expresses the moment at the ends of a member in terms of rotations and displacements. By applying equilibrium at the joints, we can solve for the unknown displacements and then determine the moments. 2.4 Moment distribution method. Developed by Hardy-Cross, this iterative method was widely used before computers. It balances moment at joints by distributing unbalanced moments among connected members until equilibrium is achieved. This method was revolutionary and still serves as a teaching tool. 3. Energy methods in structural analysis. Energy principles provide powerful tools for analyzing both determinate and indeterminate structures. Strain energy is the energy stored in a member when it deforms under load. By applying principles like Castigliano's theorem, we can calculate deflections by differentiating the strain energy with respect to loads. These methods are particularly useful when calculating displacements at specific points, especially in indeterminate structures where compatibility requires precise deflection values. 4. Influence lines. An influence line shows how a response function, reaction, shear force, bending moment, or displacement at a specific point of a structure varies as a moving load traverses the structure. Influence lines are crucial for structures such as bridges, where loads move rather than stay fixed. For example, the influence line for reaction at a support of a simply supported beam is a triangle, with maximum effect when the load is at that support. The influence line for bending moment at midspan shows the effect of placing loads at different points. Engineers use influence lines to determine the worst load positions that cause maximum internal forces. This is essential for safe and economical bridge design. 5. Stability of structures. Another key concern in structural analysis is stability. A structure may satisfy equilibrium but still be unstable if small disturbances cause it to collapse or deform excessively. Stable structure returns to equilibrium after disturbance. Unstable structure moves or collapses after disturbance. Redundant structure provides more restraints than necessary, leading to indeterminacy but usually greater safety. Stability is especially important in tall buildings, slender columns, and long-span bridges. Buckling is a common stability issue in compression members, where sudden lateral deflection can occur even if stresses are below the material's yield strength. 6. Dynamic analysis of structures. While much of classical structural analysis deals with static loads, in reality, many loads are dynamic. Earthquakes, wind gusts, moving vehicles, and machinery vibrations all produce dynamic effects. Dynamic analysis considers natural frequency, the frequency at which a structure vibrates if disturbed. Resonance occurs if external loading frequency matches natural frequency, leading to dangerous vibrations. Damping, energy dissipation mechanisms that reduce vibrations. For example, the failure of the Tacoma-Niles Bridge in 1940 was due to aerodynamic instability, a resonance phenomenon amplified by wind forces. This tragedy highlighted the need for proper dynamic analysis. 7. Modern computational approaches. With the advent of computers, structural analysis has undergone a revolution. Today, manual methods are mainly for education and conceptual understanding, while practical design relies heavily on computational tools. 7.1 Matrix methods. The stiffness method, formulated in matrix form, allows for systematic analysis of large and complex structures. It is the basis of software like SAP 2000, ETABS, and STAD Pro. 7.2 Finite element method, FEM. The FEM divides a structure into smaller elements connected at nodes. The behavior of each element is defined mathematically, and then assembled into a global system of equations. FEM can handle irregular geometries, complex loadings, and nonlinear behavior. For example, in analyzing a high-rise building under wind loads, FEM can model not just beams and columns but also slabs, shear walls, and connections in great detail. 8. Structural safety and redundancy. One of the key insights from indeterminate analysis is that redundancy improves safety. In determinate structures, if a single member fails, the entire structure may collapse. But in indeterminate structures, loads can redistribute to other members. For instance, a continuous beam over multiple supports can carry loads even if one span weakens, whereas a simply supported beam would fail immediately if a support is removed. However, redundancy also means that internal forces are sensitive to support settlements and temperature changes. Thus, engineers must balance safety with serviceability. 9. Case studies in structural analysis. To make the subject more concrete, let us consider a few real-life applications. Suspension bridges. These rely on cable action, where the majority of load is carried in tension. Analysis involves both static and dynamic considerations due to moving vehicles and wind. High-rise buildings. Structural frames must resist both gravity loads and lateral loads due to wind and earthquakes. Indeterminate frame analysis and FEM are essential. Industrial structures. For structures like chimneys or transmission towers, stability against buckling and dynamic effects like vortex shading must be analyzed. These examples show how the principles we study directly affect everyday structures. 10. Future directions in structural analysis. The field continues to evolve with new materials, new construction techniques, and new computational capabilities. Emerging trends include performance-based design, where analysis not only checks safety but also predicts how structures will behave under extreme events. Nonlinear analysis, accounting for plastic behavior of materials, large deformations, and contact problems. Integration with building information modeling, BIM, where analysis models are directly linked with architectural and construction data. Artificial intelligence in structural health monitoring, using sensors to track the performance of structures in real time. Thus, the scope of structural analysis is expanding beyond traditional calculations to continuous performance assessment and smart infrastructure. Conclusion to Module 2. We have now completed our journey through structural analysis. In this second module, we examine statically indeterminate structures, advanced methods such as slope deflection and moment distribution, energy methods, influence lines, stability, dynamic analysis, computational approaches, safety considerations, and future directions. Combined with Module 1, you now have a comprehensive understanding of both the fundamentals and advanced aspects of structural analysis. The subject blends theory, mathematics, practical intuition, and modern technology, all aimed at ensuring that structures we design are safe, serviceable, and sustainable. Remember, structural analysis is not just about solving equations. It is about understanding how structures behave under real-world conditions, anticipating possible failures, and designing with both economy and safety in mind.